This week, again, we only had one person sign up for a talk. So let me encourage you, if you don't want to hear me every time, other people that need to sign up. Yeah, I guess. We only have, I think, one talk scheduled for next week also, so it's important for other people to sign up. Otherwise, how can we keep current if no one will show us how? Right, so I put together a small presentation here. Let's see if this actually works. On one of my unfavorite subjects, which is the C programming language. So I'll tell you something about making C less dangerous, because C is in fact quite dangerous, but you got to use it, which sounds weird. I mean, if it's so dangerous, why don't we just use something better? And maybe these days there are better things out there, but there's a lot of legacy code written in C that you don't want to have to convert to something else. And the best example I know is the Linux kernel, which is almost entirely in C. And so much of what I'm going to show you has to do with what people have done in the Linux kernel to make things safer, even though they're using C. So there's a bunch of references. These slides will be available on the Keeping Current website. And so you can then use these pointers if you want to see what the original content was that I took from. So there's a bunch of different problems. And one that I didn't really know about until I started looking at this is the problem of strict aliasing. Now, aliasing is if you have two names for the same thing. And the example I have here is, let's say I've got a message type, which has got two integers, which we'll call A and B. But I also have a buffer, which is a buffer of longs. It's a different type, which is pointing to that message. Well, what can go wrong? Certainly there's alignment problems, and there's knowing that one long might hold two integers, but that's not the problem that I'm going to address. The problem is that the compiler might decide, if you're in a loop, that message.a, which I'm using over and over again in a loop, really belongs in a register. And the compiler does not recognize that that's the same thing as buffer sub 0, or part of buffer sub 0. Because they look like they've got different names. It's an alias, two different names for the same place in memory. But the fact that one of them is being cached into a register by the compiler to make things fast, and the other one isn't, means that if I change a value with one name, it does not change with the other name. And therefore, access to the buffer might not use the register. Or it could be the other order. It could be that the buffer sub 0 is in a register, but message.a is not in a register. And therefore, they're not kept synchronized. And this leads to programming bugs. It's the problem of aliasing. In fact, it's the problem which is given the fancy name strict aliasing violation. So what are you supposed to do? Well, what you're supposed to do is you're supposed to use a union. In union, there is strength. And the idea here is you can put both of these things as different fields within an overlapped union. And the compiler now recognizes that these are different names for the same thing. And will be careful about putting parts of it in registers and not realizing that the other is also modified. So here I've got, again, the message, which is a struct, and I'm overlaying it in a union with an integer as buffer, actually it should say long, as buffer, size of message type over size of long. I didn't change the slide when I changed from int to long. The problem is especially severe if the underlying types here int, here long, are different from each other. That makes the problem worse. And so I changed that to long. I should change this too. Another worry has to do with endianness. Now, you've all read Gulliver's Travels, and you all remember the town of Lilliput, where there's a big war between Lilliput and the neighboring island as to which side you open up an egg at, with the big end or the little end, and they had a war over endianness. Well, there's no obvious order for bytes within a multi-byte integer, and some computers put the least significant bytes first in memory, and some computers, those are called little endian, and some put the biggest byte first. And there's no right or wrong, you don't have to fight about it, but you have to know which endianness you're using. Well, the same problem then can appear if you are overlaying an integer with characters. An integer might be 4 characters long, but which character do you get first? The most significant or the least significant? And if you depend upon one or the other, you are now writing platform-dependent code. If you're writing an operating system like Linux, you don't want to write code that is platform-dependent because you want it to run on all sorts of platforms, both big endian and little endian. So you've got to be very careful about that when you are aliasing 2 different ways of getting at the same data. Another problem in C has to do with undefined behavior. The current C standard says certain things are undefined, and if you do it, you get what you deserve. For example, if you do not initialize a local variable in a function, well, C doesn't initialize it for you. You get whatever is in memory there. And typically it's whatever garbage was left by the last time that piece of memory was used. Why did C do that? There's actually a good answer. There's a time cost in initializing stuff. And if you plan to do your own initialization, then it's a waste of time to set it to 0 for the compiler to have set it to 0. And the C folks have always been interested in blazing speed, and so you don't want to waste time doing that. On the other hand, it can lead to errors. There is a fix in GCC. You can say, I'd like you to initialize a local variable. Now, it's going to be a time cost for that. But it will save you from uninitialized variables. What's the answer in Java, by the way? Are local variables initialized? The answer is it depends. If they are instance variables of a class, then they do get initialized. If they are local variables to a method, they do not. So I think maybe that's even a worse answer.
Why did they do this?
Why did they do that? I cannot explain why there's this inconsistent initialization in Java. Another undefined behavior is if you have a void pointer to a callable typed function. This is actually a type system weakness. If you've got a pointer to a function, you don't have to specify what is the signature of that function. By signature, I mean what parameters it takes and what return value it gives. You can just call it, because the calling routine, the assembly language you build, doesn't depend upon how many parameters or what the return is. However, it's a type system weakness. Another undefined behavior is a poorly designed library routines, like memcopy, which has no length parameter. You just say copy from here to there, and it'll, is it memcopy? Yeah, I'm not sure it's memcopy, but most likely it is. It goes until it sees a null, but you might go too far because your destination might not have enough room. Maybe it's stir copy.
Yeah, stir copy.
Okay, dynamic length arrays. If you can declare in C an array whose length is determined by a variable at runtime. And so here I've given it the value 8192, 8K, and I've declared it. And then I can go beyond the end of the array. I can have a negative index. And this is very expensive to do bounds checking. Well, in general, arrays, what if I had said here, 8192? Well, then I could hope that if I put an explicit value here, which is clearly outside of the range, the compiler will say, no, I know that's out of range, you cannot do it. But it doesn't even know what the range is at compile time if I have a runtime value here. And you can do all sorts of bad stuff this way, accidentally or maliciously if someone's inserted code. You can overwrite the return address. You can overwrite someone else's stack frame. You can even circumvent guard pages and stack canaries. How many of you have heard of stack canaries? It's a great idea. It says that right before you return, you have something on the stack which is a compile time known constant. And right before you return, you make sure that that's the constant you expect when you look there. If someone has intentionally or maliciously gone past the end of an array, that value will have changed. And you can say, there's clearly a problem. My canary has died. I'm getting out of this mine immediately and get overboard. However, if you can access not by overwriting an entire buffer, but just going to a random place, you can go beyond the canary. And it also turns out that the code for accessing this kind of an array in C is actually slower. And I saw an example of the number of lines of assembler code necessary to access it. It's about 4 times as long to access one of these dynamically length sized arrays. There's also a warning. Warn for VLA, which stands for variable length array. I prefer calling it dynamic length. It's not really a variable length, it's a dynamic length. But the world seems to call it a variable length array. All right, a terribly designed case statement. Well, in Pascal, and in LLW, it was called a case statement, and they did it right. In C, they called it a switch statement, and they did it wrong. Not only did they change the name, but they did it wrong. In a switch statement, you have an expression, typically an integer, and you have a bunch of cases, depending upon what that integer is. And this can be made to be very, very fast, because you can build a jump table. If it's integers from 1 to 10, you can build a little table, and the compiler builds a table of which, and it just indexes into that table for 1 and for 2 and for 3, and each of those goes to a different piece of code, nice and fast. And it's usually faster than an if then else, if then else, if then else. Although the compiler can choose to compile it into that if it wants. The problem with the design is that each branch, once you've finished with that branch, does not automatically finish the statement. Instead, it can fall through to the next branch. The default in C, and in Java, and in JavaScript, is to fall through to the next branch, which is almost never what you want. In Go, which is a new language, fairly new, by the Google folks, you do not fall through by default. Once you've finished a branch, you've finished. In the unusual case that you want to fall through, in Go, you say, I want to fall through. And it's explicit then. But in C and its related languages, if you don't put in a break, you just fall through to the next one. Now, there is a warning you can turn on, implicit fall through. What you should do is, if you have an intentional fall through, you mark it with a comment. But people who use a lot of case statements often forget to do that and don't put in this implicit fall through. Later, I'll tell you about how it looks in the Linux kernel.
Is the problem there mainly with human error, or is there?
It's human error. It's programmer error. It's a fragility in the language design that makes it likely that a programmer will do it wrong. That's right. And there's an unrelated error that if you've got a switch statement and you have automatic initialization, which you might want, what happens if you put the variable declarations between the switch and the first case? It turns out that that's not executable. It doesn't happen. Although the syntax allows it, in fact, it doesn't do any good. And therefore, you really want a switch, you want a warning for an unreachable piece of code there. And there is such a warning. I tell students that you always want -W all. Turn on every single warning. Because instead of remembering all the different things that could go wrong, just tell the compiler, I want you to warn me about anything that I might have done. an interesting question. There are times when you want arithmetic to overflow. If you're computing the hash value of something, you're most likely doing shifting and adding and multiplying, shifting, adding, and multiplying. And you want that overflow to happen. You don't want anything to be interrupted. Also, the hardware is not going to give you a trap when there's an arithmetic overflow, because hardware designers have decided that it's so likely that if you're not interested in seeing the overflow, we're not going to generate a trap. So if you want to check for overflow, how do you do it? You've got to add extra code. The compiler then has to add extra code after every arithmetic operation to see if it overflowed. Overflew? Anyway, so if it's signed integer, you almost certainly do not want overflow, and you want it to be flagged as an error. If it's an unsigned integer, chances are you don't care. All right, so you want to very likely then turn on a warning, but it requires extra code. Now the code is possible. Here's the GCC fix, sanitize equals signed integer overflow. It turns out that it's not that expensive in time, because all you've got to do is after every operation, check one flag, at least on the Intel. There are 4 flags that are set by every arithmetic operation, and one of them is there was overflow. We can just check that. However, having the warnings does increase the total code size. So it's fast, but bulky, and you might not want that. One suggestion is that you can, in those places where it's important to you, you can have a macro, check add overflow, add A to B and put it in C. And if that is overflow, then you might want to return some sort of an error. And this is explicitly more expensive than just A plus B. You put it in those places where overflow is a problem. All right, bounds checking. Everybody touched on this, but C, array indices are not checked for bounds. And so the first problem is off by 1, because C arrays start with 0. So if your array is of length 10, it goes from 0 to 9. But if you've got a loop that goes 0 up to and including 10, you've made a mistake. You've gone 1 past the end, and the compiler likely is not going to help you with that. And you're going to go 1 past the end and do whatever it is with that last non-existent piece of array. It's a fault in the language. So that's easy to make a mistake. Negative indices are also valid. They're usually erroneous. It just because of the way C defined arrays. Now in Java, it's completely different. In Java, all array accesses are checked. In Pascal, you can turn it on or turn it off. There are 2 schools of thought as to whether you should turn off array checking. Certainly while you're debugging your program, you should turn on array bounds checking. When your program is in production, what do you think? Should you leave it on, which is going to cost you in time, or turn it off, which is going to make it faster? Well, the metaphor I like is, it's like carrying an umbrella, but leaving it at home when it's going to rain. We've got this umbrella, this protection. When is it going to rain? In production. You should most likely bring your umbrella with you in production. That's my point. Java always has these checks. I don't think you can turn them off. Yeah, Jim?
So what's a good example of using negative indices in a good way?
Yeah, when do you really want to use a negative index? When you know the memory layout, which you're not supposed to know, and you've got 2 data structures next to each other, and the second one is an array, and you really want to talk about the first one.
Yeah, I have a hard time saying that's a good way of using it.
Yeah, it's a bug in the language design that it allows negative indices. Now, inside the Linux kernel, there are a few places where they very carefully check. When you're copying data from user space into kernel space or the other direction, it's very carefully done with sizes. And if it's out of range for whatever reason, there is a check. It turns out to be pretty complicated the way it's implemented in the kernel. But it doesn't have a very large speed cost. And there's versions of strcpy, strcpy, where you specify the length. It turns out that people have found problems with strcpy, which I never knew of before. One is that if you're you shouldn't use it for strings. But it says stir. Well, it turns out that if you have a string of length 10, and you say stir UKY 10 into a destination, it's going to copy the 10 characters, but it's not going to copy the null. And you end up with an unterminated string. So what you should be using, it also null pads whether you want it or not. Okay, you should be using stir UKY, which will guarantee to put at least one null at the end. But even that has its problems. People have started talking about stir SKY, which supposedly is even better. But there's a cost, of course, in checking the length. What you really want is hardware memory tag. What you want is to say, this region of memory, this array, has a particular key associated with it. And every time I want to access it, I provide the right lock for that. And in the hardware, it makes sure that my lock matches the key for that data region. And if it doesn't, the hardware says no and gives me a trap. That's the right way to do it. That requires hardware support. Intel doesn't have that. It is available apparently on the Spark. When was the last time you used the Spark? We got rid of all of our Sparks a while ago. Yeah.
Why do like so many people depend on the negative indices feature that they are choosing not to fix that bug?
Who can say? But the index, you see, is known only at runtime. And so if you'd have to add extra code to say, if index is negative, do something different. Because the calculation for where to go into the array is done by a single instruction, typically in the Intel. But it allows a negative value.
So it's just adding two numbers that you don't know if those
Yeah,
numbers
that's
are
right.
negative.
Adding a little multiplication for the stride. Yeah. When did we finally get rid of our last Spark, Paul?
Oh, I want to say 10 years ago.
Yeah, no one uses these anymore. All right, there's something called control flow integrity, which has got two directions. If you're calling a procedure, there is two edges. The forward edge, as you call it, and the backward edge as it comes back. And it turns out that there are risks in both. The principal risk as you're calling something is that if the method is somewhere in the heap, that is you've carved out a data structure and you've got some code sitting there and you want to call it, it's very difficult in C to do it in a typed, secure way because you don't necessarily know or can you check that you're calling something of the right type. And you might accidentally call something which has been overwritten by something else. You might go to the wrong place in the heap. It's really risky to call something which is in the heap. Backward edge vulnerability has to do with the return address. If some attack is able to overwrite the return address on the stack, then I might not go back to whoever called me. I might go back to something else. People have thought about ways of preventing this problem. And one really nice idea is called the shadow stack, where off on the side you have another stack which only holds return addresses. And the first thing you do in the prologue of a function is it copies its return address before anyone has had a chance to modify it. Copy the return address onto the shadow stack. And as it's about to return, instead of just returning, and the return address is right now where the stack pointer is pointing, instead it first checks, is that what I've got on the shadow stack? Pop what's on the shadow stack, check it against what's here, and if it's different, someone has been interfering. And there is something in CLang. Now, CLang is a competitor to GCC. And there is something called sanitize equals shadow call stack, which automatically puts in the necessary code for that. There is going to be a cost for that. There actually is hardware support in the ARM. And there is something in GCC called sign return address. And I can't give you any more details because I don't know any more details. Look that one up yourself. So what have they done in Linux? Well, there's something called the Linux Kernel Self-Protection Project, or the KSPP. They left off the L for some reason. And the purpose is to protect the kernel from bad things. it's mostly written in C, generates nice, fast code. What is not in C, it's even worse, it's in assembler. So what's the status of that project? Well, variable length arrays, they say they've nearly eradicated them. How about switch branches? Steady progress on marking where it has to fall through. I looked at the statistics. About half of them are still there, haven't been fixed. All you need is an RA for a semester, right, to fix all that? I don't know. How about always initialize local variables? Oh, they're waiting for the compiler to do that for us. Overflow detection, explicit arithmetic for memory allocation. They have it only, overflow detection only when they're allocating memory. When you have to compute how much memory you're allocating from an allocator, in particular something called the slab allocator, you have to do a computation. What if the computation overflows and gives you a negative number? Bad. Well, they do check there, but they don't seem to check anywhere else. Bounds checking, oh, we'll wait for hardware support because it's just too hard to do it ourselves. Forward edge control flow integrity, it already is fine on the Android. Why? Because it's on an ARM processor and it's got the necessary instructions. Backward edge control flow, shadow stack, they've got it on the Android, but they're waiting for their platform. So they're getting there, but there's still going to be problems, and there's still going to be bug reports based on things that have gone wrong because of incomplete protection. Now, people have thought about variants of C that make this better. Originally, you say, well, C is just a portable assembly language, and I'll heavily use ifdef and autoconf to make it work on every machine. ANSI C, which was already in the last century, was a compromise with a lot of enhancements to provide type security, in particular, ability to forward declare procedures with the full signature. Pointers are still going to be awful. And it was there that the concept of undefined behavior was introduced. That some things are declared to be undefined. For example, what if I've got a long int, a 64-bit int, and I left shifted by 64 bits? What's the meaning? On most machines, it's a no-op. But it's allowed, it's undefined, so it's allowed to crash, it's allowed to subtly corrupt memory, it's allowed to connect to a server to transfer money out of your account. It is undefined what it's doing. Likewise, signed integer overflow is undefined, a bunch of stuff which is undefined, and there's a whole archive where you can look at about that. Now, my own addition to this. Bad language design leads to all sorts of fragile code. Operators that look the same but can be used, whenever one can be used, so can the other. One of the worst bugs I ever tracked down was an assignment statement which said A equal 3. You keep staring at it, it looks like an A gets 3. But in fact, it's comparing A to 3 and throwing away the result. The fact that you don't have to use curly braces on the branch of an if or the body of a for. You always should. But if you leave it out, it's correct. The danger is that someone might actually put a semicolon before the body, especially if the programmer is a PL1 programmer. Then you have an empty body. Or a maintainer who wants to add another line to the body and doesn't realize that we've left off the curly braces, just put something else at the right indentation. Works great in Python, doesn't work at all in C. The fact that you don't have to have function prototypes. How's this? I hate the auto increment operator. What does that do? Nothing. It takes the current value of J, adds 1 to it, and puts the original value back in J. But at first it looks like it increments J. Advice, never use plus plus. And even more so, never use minus minus. The fact that arrays are just pointers, that is a terrible design decision. If you pass an array to a function, the function just gets a pointer. It has no idea how big the array is. Now there's even no way to check. Even if you want to check array bounds, that information is gone. And the fact that strings require an alternative. You've got the length of a string, and you do an m-alloc, so you can hold it. You always have to add the 1. You forget that, and everyone does, you now haven't allocated enough space. So, there are all sorts of fragilities in C. My advice is, if you've got to write a new program, do it in a different language. Many things are better in Java. Most things are better in Go. There are other alternatives too. But keep current. Don't use C unless you absolutely must, like if you're maintaining old code or writing inside the Linux kernel. That's all for today. See you next week.